Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this talk is about environmentally immersive programming, and it's something that we started to do at the University of Virginia, and recently as I moved, we're continuing to do that at the University of Illinois. Why we're doing this and what's so, why I believe it needs to be done. Well, if you look at where is the cost in developing sensor network systems, if you look at one particular experience I had, and that's with Jack Stankovic, we built this VigilNet system at the University of Virginia. Jack Stankovic was the PI. And so if you look at what did the system cost, well, the hardware for the system cost something like $10K at most. It was 100 nodes, well, maybe a little more, and at market prices, you can buy that for $10,000. Now, the software development was a really big effort. And so if you look at the most optimistic estimate of what it took to develop the final version of that software, it took probably at least 5 grad students who I would say worked hard for 20 weeks, full time. And I guess you can employ grad students pretty much for free, but I put $30 an hour there for them. So if you multiply that out, you get more than 100K just developing the software. So essentially, software development is really the big hit as opposed to hardware. And hardware is getting cheap, whereas programmers' time is not necessarily getting much cheaper. So we need to solve the software development problem. We need to make that easier, cheaper, and so on. What does that entail? Well, first, we need to remove or to reduce the cost of actually coding, writing down the software. And so we need to structure the code, and I agree with the previous talk in terms of you need to really have some kind of reusable components there in order for you to be able to develop applications pretty quickly. You also have to have suitable high-level abstractions so that those who actually write the code are able to write that easily and not in an error-prone fashion. Another huge cost is debugging. I mean, we spent most of our time not necessarily building the software, but really debugging it. And so you really need some automated checking and analysis tools that are able to find incompatibilities between different components and are able to resolve these incompatibilities. Another type of debugging here is sort of performance debugging, because there is a lot of services that run in a very resource-constrained environment, and you put them together, you run them, and perhaps you don't get fast enough response, or your capacity overflows and you get congestion. And so these types of performance debugging needs to be addressed as well. So there is a substantial testing cost involved, and that testing cost needs to be minimized. And the way you would minimize it is perhaps do something like MSTAR or other simulation/emulation environments, perhaps integrate that with your software development environment so that a developer can sit, program to these high abstractions, and then have an analysis engine that would say, well, here are my sort of performance requirements on the system. Would this code satisfy those requirements? And then there is a collection or a mix of analytic techniques and simulation-based techniques that come back and say, well, you have bottlenecks here, and you're likely to have problems there, and you have incompatible assumptions between these types of modules. Please fix that. And that will hopefully reduce the cost of developing software. So we're trying to build a system that would address these issues. Okay. Now let's start with the first level, which is the high level of abstraction. And there was a lot of work on making distributed programming or programming to a distributed environment easier. Now that work traditionally focused on abstracting communication, for example, in a distributed system, and providing things like location transparency. Okay, so a lot of the traditional paradigms for distributed computing, if you will, address these two items. Now, we believe that in a sensor network that alone is not enough, because the main function of a sensor network is to understand something about the environment. And that is why it's programmed. That is why the code is written. And so the code should somehow be revolving around environmental abstractions directly, that would simplify and make it more logical for the programmer to conceive of what needs to be written and how it needs to be done. So essentially, in a sensor network, we really need to represent, we need to have a computing paradigm that would represent the physical world in an easy and an intuitive way to the programmer who actually writes the code to access that world, and facilitate the distributed interaction, facilitate writing or coding the distributed interaction between the sensor network and its environment. Okay, so you can think of an environment like in that picture here, and perhaps every object that is being sensed in that environment is represented by a logical object in the computing system. These logical objects will make it easier for the programmer to assign tasks that need to be monitored about them, or how they should coordinate. So there's been a lot of there's been a lot of effort on writing different types of high-level abstractions, high-level programming abstractions. And this is a partial list. I haven't really updated it. But there's been several of these languages. What I'm going to talk about in this talk is something we call Envirosuite, where the focus is on abstracting the environment and representing physical objects in the environment by logical objects in the computing system. And if we believe that that is a reasonable abstraction of one of many reasonable abstractions, well, what are the challenges in actually implementing it? Okay, what are the challenges of building a programming system around it? So to repeat the abstraction, we want to present this new address space. We want to present this new address space to the programmer where the addressable entities are, in fact, representation of physical things in the environment. Now, these physical things could be, in a target tracking applications, could be, for example, targets, cars driving around, and you want to represent each one by an object in your computing system. If it's something that collects data from a big region, maybe that region is the object, and you want to represent somehow the state of that object. Maybe you have multiple regions, so you have multiple region objects. In a ubiquitous type of computing environment, perhaps the objects are self-identified. So maybe this room is an object, and maybe people are walking around with RFIDs, and they self-identify that I am, person X, and that would be an object. And then you can operate on these objects and, for example, find out which room a particular person is in. Okay, so that is the idea. We have this context. They have some kind of logical representation. They have a unique name. These contexts are instantiated dynamically when, say, in a tracking application, a car drives into the environment. The system should generate that object dynamically for the car. And you can attach computation. As a programmer, you can attach methods that would execute in these contexts. And that's how you build your application. So, okay. So essentially build a system that does or begins to do these tasks. And that system is composed of several parts. The first part is kind of a user interface. So the user writes in this new language, which is Envirosuite, and these declarations are translated into application code, which in this case is actually written in SC. It also gets translated into a whole lot of library calls that do various things implement various types of support protocols for representing different types of objects. Let's see. Beneath that interface, there are a couple of levels of abstraction. So at the very low level, we're abstracting away the sensor data processing protocols. So even the simplest sensors, like magnetometers, for example, or light sensors, or distance sensors, may have outputs that are pretty sophisticated sinusoidal waveforms, and you need to mine these waveforms for certain patterns to, for example, realize that you have a motion hit, and that hit is in fact a large target and not, for example, a small target. So there's a lot of work that's been done on doing these types of data processing on the modes. And for example, there's a paper by Jack Stankovic on that on Census 2005. There's also things like these micro cameras. You do get visual feed from the environment, but you don't actually send those frames out. You represent them by a very kind of concise representation. And so this interface above this layer is really very concise. It's a short representation of essentially a complex phenomena that's been filtered out. And that comes from multiple sensors dynamically at runtime. Now, every type of object, now, EnviroSuite has a taxonomy of the typical objects that you might encounter in the system. And as we encounter more applications, we can extend that taxonomy. So as I mentioned before, I gave examples of tracking objects where you track something that is actually localized but moving in the environment. You have region objects, which is something very diffuse, and so on. Representing these objects requires different types of protocols. So for the tracking, you will have protocols that support for migration so that you get to track, your state gets to track the object that is moving. For region objects, perhaps it's going to be some kind of a tree formation protocol. So every type of object will have its own representation protocols in the EnviroSuite system. And that's what these protocols are. Also, we don't necessarily assume that we have a base station. So it could be that the data that is generated needs to be locally stored, but it needs to be locally stored in a way that we can find it later. So we need a distributed storage system where we can operate disconnected for a while, but then once you put a base station, the base station can suck up all the information in a meaningful way. Or perhaps somebody can walk into the system with a PDA and communicate with the nearest node and be able to find out what had happened in the system when it was disconnected. That also requires a communication system, and it sits on top of the regular Berkeley stack. So that is the, a kind of a small summary of the main components of EnviroSuite. There is also an analysis engine because, like I said, one of the things that we're trying to do is to facilitate performance analysis so that a programmer can say, look, here are my performance requirements. Can I really meet that? And so the programmer would specify this. There's an analysis engine that would interact with my protocols and be able to say something about whether or not performance is likely to be met or not. And that may also interact with the simulator. So I am able to develop this code, compile it, and then simulate it on something like TOSIM. Right now, TOSIM is not necessarily representative of performance, but it will give me some idea of how this thing will work. OK, so what this achieves is I have now been able to transform the programming task from the level of writing these distributed protocols, which are very error-prone and something that the programmer typically doesn't like to do, transform that into writing aggregate things. And I'm going to talk about the programming model. So essentially, I'm going to be saying things like track vehicles at a high level of abstraction. And that will get translated into, oh, that's a tracking object. I know the protocols to do that. And I know what type of sensory data I need to use. So the programmer's life has been easier. The programming code is much shorter. Hopefully, it's less error-prone. And I have analysis tools to make sure it's correct. So let's look more at the language. This is really more of a preprocessor rather than a full-fledged language because we do write in NES-C, but we augment NES-C with the ability to declare new types of objects. So there is this extra set of declarations that the programmer writes up front, and these declare contexts. So from the programmer's perspective, what they write are the types of contexts, and I'm going to talk about what that means, and the type of state that they want to collect in each context. And so these contexts perhaps would be for objects of different types. So here's an example of a context of type car and a context of type human. And they would be defined by different sensory signatures. And so at runtime, when the compiled EnviroSuite runs on the modes, whenever the modes find that the sensory signature matches the ID of one of the objects that they learn about from the compilation, a corresponding logical representation is constructed. And then from the programmer's code, the programmer has defined what types of methods run in what type of contexts. So these methods are automatically instantiated in that context. Okay? Now, these methods may work on certain state that, again, the programmer defined so that it's collected within this context. There may be multiple objects that exist together. And so there are inter-object communication primitives that allow the programmer to exchange information. So, for example, can count cars. Now, note that the way that would be implemented, it can also work even if the system is operating unattended and disconnected. So it doesn't have to have a base station, although having a base station would help. But if there's no base station, it can still survive. And then when the system gets connected again, the base station can suck up the information that was stored in the system while it was disconnected. Now, this is a pseudocode of just to give a hint at what would it take to write a context. So essentially, you specify two things. Let's say you want to specify a context tracker for this car. You just specify two types of things. One is the sensory signature, what it is to be a car, and a state. What do you do when you see a car? So this was, the origins of this started in this DARPA project where we were tracking vehicles and people in the desert. And so perhaps if something is moving in the desert, that's already a potential problem. And if it has a magnetic signature, then it probably is a vehicle of some sort. And so maybe those, and these are complex functions. So this is not necessarily, this is a complex signal processing algorithm, perhaps that runs on the modes. So that describes the signature. Now, everybody who matches this signature will say, well, maybe I am seeing a car, so let's form a group. They form a group, elect a leader, and this leader starts collecting data about the car. Which type of data? That is what the state function specifies. So in this example, it collects location, in particular the position of the sensor that is reporting the event. And you can associate some quality parameters, like it can say that I need at least 3 sensors to tell me there is a car in order for me to believe that it's a car, and perhaps I need them to report that within the last 2 seconds. So there has to be 3 concurrent within the last, say, 2 seconds, some kind of freshness parameter, in order for me to remove false alarms. That defines the context, and it defines what data is encapsulated. It doesn't define what necessarily to do with this data. So that's when the programmer writes objects and attaches these objects to the contexts. Okay, that's done at compile time. So this generates the compiled program that gets distributed on the modes. To summarize, the programmer writes 2 types of entities, the context and the objects. The programmer then attaches objects to contexts, and they can communicate. And so at runtime, when the objects that the sensor network knows how to identify are found in the environment, the nodes automatically form the logical representations of those things and be able to exchange information.
In your specification at compile time, such as how many sensors to use and so on, so assume that you actually have a model of the deployment at the compile time, or is that realistic to have? How do I decide that 3 sensors are needed in a particular geometric
situation?
Yeah.
So that's where, if you notice in the beginning, I had this box on the side that says analysis. And so that's where that box can say, you need at least 5 sensors given the assumptions that you told me about the environment.
But you also need actually a deployment model, that is where the sensors are.
That's right.
And
That's right.
Available.
That's right.
You need some discovery phase that feedback into your program.
That's right. So in this case, for example, if you put the sensors far enough apart that at any particular time there's no more than 2 that are seeing the target, and you said I need at least 4 to believe you, then you're never going to see any targets. But you do have, for example, things like the probability. You can compute the probability that a sensor is going to give you a false alarm.
I thought that would be actually a more interesting goal at compile time. That is that you specify the data fidelity at compile time, and then at the runtime to instantiate into a particular configuration.
That's right.
As versus that specify the number of sensors and so on at a compile time, which seems to be very hard.
Yeah. So what happens with the actual EnviroTrack code is that it does return, saying, okay, I have seen the target and there are 3 sensors, and so if it's below your threshold of say 4 sensors in order for me to believe you, then you can choose to not believe, or you can choose to believe. So it basically returns both numbers. It says, here's an object that you requested with, I want 4 sensors for it, but I got only 3. That's all the object. Okay. So that was a brief tour through the programming model. Now, each type of object has its own sort of object representation protocol. And let me give you a brief hint of an object representation protocol for the tracking objects. Now, what does the object representation protocol actually does? What it does is, first of all, it has to ensure unique representation. If I see one car and there are 5 sensors that I see in the car, I should still report one car and not 5. So there are protocols to ensure unique representation. It's a little bit harder is to ensure identity management. If I see 2 cars and those 2 cars cross roads, cross paths, how do I make sure that I actually associate the right identity with the right car after they have crossed? And for certain types of sensors, that is simply impossible. But that is one of the challenges. One thing that is good about having predefined protocols that do these things is that you can have fixed semantics. You can understand exactly what these protocols will do when they are crossing targets. You can understand a little bit more about false negatives and false positives. And you can understand a little bit more about how these protocols will define, for example, object boundaries. So one of the advantages of using the system is that you are using protocols that have been pre-tested and that have been associated with certain semantics that you can rely on when you are building systems on top of them. Now, these protocols would be defined into multiple categories depending on what type of objects they are representing. And let's take an example of tracking objects. So the actual protocol that we use for tracking objects is that whenever a bunch of sensors sense the object, so you have specified what it means to sense the object, whenever that is true, these sensors will form a group and elect a leader. This leader will then broadcast and say, I have seen an object of a particular type, and I have given it an ID, and here's the ID. So now everybody within a slightly larger radius knows about the object. Later on, one of these yellow nodes might, so these red nodes, imagine these are the ones that see the object now. The yellow nodes are the ones that know about it from the leader. If one of the yellow guys later sees the object themselves, they are not going to create a new representation for it because they know that it's probably the object that they just heard about from the nearby leader. So that reduces the problem of creating spurious objects for the same physical entity. It also turns out that there is a limit on how fast that external entity can move without creating spurious representations. So the intuition is that if the external object moves too fast, then it's going to be detected by sensors that are so far enough apart that they cannot realize, they do not realize that they're seeing the same thing. Okay? Whereas if the external object moves slow enough, then it's easier to recognize that we are all seeing the same external entity. Okay? So we are able to quantify what that maximum trackable speed is. Okay. There are all kinds of open questions in how to ensure unique representation of these things. How does that unique representation depend on object type, for example? Are there any fundamental limitations? So, for example, if you look at unique representation, it's something like a consensus problem. We'll have to agree that we all see the same thing. And so there may be some fundamental limitations with achieving these types of consensus among nodes at runtime. And so how can the runtime system automatically verify that unique representation will be achieved or not? Now let me give you very briefly another result. So this is in the analysis. So I'm shifting gears from sort of the unique representation of objects in the physical environment to something that we can say about the relations between throughput, for example, energy consumption, and delay. So in general, a programmer must specify performance requirements, and I need an analysis engine that is able to tell me whether these performance requirements can be met. And I'll mention very briefly at a high level what exactly that analysis tool does. So that analysis tool thinks of a sensor network as a cloud. In general, at a kind of bird's eye view, that cloud receives or consumes energy to convert events into some kind of actionable information. And in doing that, it takes time. And so there are really three fundamental axes in this formula. One is the axis of time, the delay it takes to process the information. One is the energy, and one is the sort of throughput, how much output I can get out of the network. And so we would like to quantify, in order to do any type of optimization, we would like to quantify what are the fundamental trade-offs in that space. Ideally, I would want infinite information in 0 time with 0 energy, but that's just not possible. So the question is, well, what is possible? Okay, where are the boundaries of what is possible in that 3-dimensional trade-off? And so we've looked at that boundary. And in particular, we looked at the boundary between throughput and delay. And I'm going to go through this very, very briefly. But essentially, we asked ourselves the question that if you have some data in the network that is time sensitive and it needs to get to the edge of the network or to a base station within a particular amount of time, how does that time relate to the throughput that you can get out? And how does that change if you have, say, multiple flows with different time constraints? So intuitively, their ability to get out of the network in time decreases if you increase the packet size, the length that you travel, or essentially if you increase the amount of data, if you increase the length that you travel, or if you decrease the latency constraint. That decreases your ability to actually meet the latency constraint. And so your ability to meet the latency constraints is affected by this factor. And it turns out that this factor has a bound. If this factor is less than that bound, you are able to meet your latency constraints. If it's above that bound, then our bets are off. And so we quantified that bound for different types of networks. Okay, so this would be an example of such a bound. And what this does is that now you can relate all kinds of network parameters like path length, how many collection points you have, what type of radio you have, to throughput that you get, and to latencies that you get. And this would be something that the analysis tool can help you with. So if you get a very, very rough back-of-the-envelope calculation of whether your network is over-provisioned, under-provisioned, it has not enough density, or what. And I'll probably stop here. Just mention that we have, in fact, deployed a larger system that was composed of this tracking slash EnviroSuite, plus a lot of other services, including time synchronization, power management, and so on. And that was part of a DARPA demo. So since everybody had a picture, I have a picture too. And we were able to track things in the environment, walking person, running person, vehicle, another vehicle, and you could see tracking results there. So it tracks relatively accurately. So to summarize, what we are trying to do is answer a bunch of open questions, such as, what are the right abstractions for high-level programming for sensor networks that would reduce the development cost? And what are the type of layers that should sit underneath that abstraction? Okay. Sensor networks live in physical time and space, and that creates those spatio-temporal constraints. And so what is the right equation, what is the right way to analyze the fundamental spatio-temporal constraints that exist in a sensor network, and the fundamental trade-offs between various properties like timing, throughput, energy, and so on. And generally, what are the right tools that would reduce the cost of things like development, validation, testing, deployment, and execution of sensor network systems? That's what EnviroSuite is hopefully trying to achieve. And that's it.
Obviously really like your modeling of energy versus capacity and latency and everything else. So I guess the question is, if you apply that to the kinds of tracking algorithms that you've got, I will assert controversially that you're always better off just sending all of the data back to a central high-powered node and computation there. Excuse me, not all. Local processing on the node for its own filtering, but the zero mode-to-mode distributed signal processing is the optimal. Am I dead wrong?
I think I partially agree with you. The one thing that might come into the picture is that in the modes that we've tried, there's a very, very high degree of false alarms even after processing. So you do local processing, you still get false alarms. To give an example, modes have this antenna, and when the wind shakes the antenna, the magnetic sensor goes off. When it rains, the motion sensor goes off, and so on. And so at some point, you can send all this data to a base station, but you can save some energy by just locally, in many cases, if you just ask a couple of neighbors, you can realize that it's a false alarm. So that level of processing, which is local to one hop, but not necessarily, if the base station is not within that hop, then it's not necessarily at the base station, can help. Yes?
Well, I have a comment and then a follow-up question. So the comment is that at one point you said that what you'd really like is you get infinite data out of the sensor network for free. That's the last thing you want. The back-end systems just wouldn't be able to deal with it.
Okay, I agree.
There's a point there, which is the system needs to be smart about what data it produces and how it assigns priority to the data.
Absolutely. Absolutely.
A related question, since this is the foundation section of the talk today, I think it's important to bring up. Everybody spoke about sensor networks with a single application. And if you think about the kinds of things that, like Deborah was talking about, $400 million sensor networks, right? These things are not going to be running as a single application. So I'm wondering if the people that are thinking about the foundations of these systems, if you thought about how to share resources across a lot of applications.
Yeah, so actually, I want to go back to the point with priorities. So one of the things that we are doing now is trying to build essentially a MAC and routing layer that does prioritize data so that we optimize some notion of utility rather than some raw notion of throughput. And in terms of the running multiple applications, that's something that needs to be addressed. So right now, we are able to simplify the act of programming the application, but it works best if you run one application at a time and download it.
Sorry, I mentioned this uncertainty whenever you send physical objects. Actually, this is two types of uncertainty. So the thing is uncertainty about the positions of vehicles, also the discrete uncertainty about the entities.
That's right.
Don't you think that should be explicitly in the programming abstraction that is as part of the definition of a track, which is the representation of the uncertainty of the track? Because the higher level application has to deal with this. I mean, you can think that the first class object in the system, not just as something that
That's right.
thinks about afterwards.
So the way we went about it, so I sort of agree in principle that the application domain expert is the one that knows the most about these types of parameters and the uncertainties about different objects and models, in particular models of, for example, this tank cannot make a 180-degree turn this way. And so right now, this is sort of embedded as a module, as a submodule of the tracking protocol, which can be swiped in and out. And so in some sense, if I go back to this picture, let's see. Yeah, this picture here. So part of this tracking protocol would be the model for the tracked object. And so you can change that module. We can make it into a first-class abstraction so that there's an easy interface for that, but in the current system, we haven't done that. Yes?
Are you changing dynamically those modules in the nodes?
What it means to track?
Yes.
Right now, the tracking protocol is fixed. So you have to choose your tracking protocol, but then you are sort of married to it while the system is tracking.
Speaking of dynamics, the network analysis is very valuable, but when you actually deploy these things look quite differently, both in time and space.
That's right.
Is there a way to update? Do you have sort of a small runtime version thereof that you can update as the thing is running?
Yeah. So you can update. So basically, this is not to eliminate the deployment cost. There will be a deployment cost. Hopefully, you will live in the field for, say, 3 days instead of a week or 2 weeks to get the system to run. And that's what we're trying to sort of reduce.